us today. I'm Kelly Kurt, Senior Digital Marketing Manager here at MPS, and I'll be joined today by our Senior Technical Marketing Engineer, Pete Millett, for our webinar, Stepper Motors and Back EMF. In this webinar, we'll learn about Electro Motive Force, EMF, and its impact on motion in a stepper motor, how to measure it, and how that measurement can provide feedback about the motion system. Before we get started here, I do want to do a little bit of housekeeping. We are recording this session, and it usually takes us a couple of days to process it, but we'll have it available for on-demand viewing in the next couple of days. We'll also have the presentation itself available for download. So you'll be able to find it at monolithpower.com/webinars, where we keep all of our past webinars. We'll also send an email out to everyone once we have it all set up and ready to go. All the attendees are muted. We will have a full Q&A session at the end of the presentation. If you mouse over the bottom of your Zoom webinar interface, you'll see there's a Q&A button. You'll just be able to click on that and ask questions there. All right, so without any further ado, I will turn it over to Pete.
Okay, thanks, Kelly. So before we get started, a little info. I'm Pete Millett, Staff Technical Marketing Engineer at MPS. As Kelly mentioned in today's webinar, we're going to talk about back EMF in stepper motors, how it affects motor performance, and how you can use it to provide some feedback about the motion system. So as for me, I've been working with motor driver ICs for about 15 years, mostly doing product definition and systems and applications engineering at MPS, and before that at Texas Instruments. Before that, I worked for a lot of years as a board level hardware engineer. So here's the agenda. First, I'll talk about the meaning of back EMF in a motor. We'll focus on back EMF in a stepper motor and how it affects motion and how it can be measured. Then I'll show how that measurement can be used to provide some feedback about the motion system. EMF means electromotive force, which is really more or less another term for voltage. When a conductor passes through a magnetic field, a current is induced in it. This current causes a voltage to appear across the ends of the conductor. Motors that rely on a fixed magnetic field from permanent magnets can also act like generators or alternators. When the windings are moved through the field, or when the magnets are moved causing the field to move, they generate a voltage across the winding. In a motor, we call this voltage back EMF. So virtually all motors that employ a magnet has back EMF. That includes brush motors, brushless motors, and stepper motors, which is what we're talking about here. So there's two common types of stepper motors, the permanent magnet stepper motor and also the hybrid stepper motor. Their construction is different, but both rely on a rotor that has permanent magnets and coils on the stator, which is the fixed part of the motor, to attract and repel the poles of the magnet. Most common stepper motors use two phases, so there's two windings, although there are also 3- and 5-phase stepper motors. For this webinar, I'll only discuss two-phase steppers. Two-phase steppers have two windings, which are driven 90 degrees out of phase, sort of like sine and cosine waveforms. Permanent magnet steppers are usually made with a ceramic magnet rotor that's magnetized with several segments alternating north and south poles. The two coils are wound on iron cores that have teeth, which are bent down from alternating sides to concentrate the flux and to give north and south poles from the winding. Two of these assemblies are stacked, one for each phase. so they get the name can stack stepper motors. Hybrid stepper motors are built differently. They use a 2-section iron rotor with small teeth and a magnet inside that makes the teeth on one section all north poles and the teeth on the other all south poles. The 2 sections are slightly offset, and then the coils are wound on pole pieces that also have teeth. Since a stepper motor has permanent magnets in the rotor, whenever the rotor is turning, there's EMF induced in the windings. So to demonstrate this, I spun a stepper motor with a power drill. The windings are just terminated in resistors. So with this particular motor and the drill running at full speed, whatever that is, I got about 120 volts peak to peak out of each winding. So the other thing you can see here is the phase relationship between the 2 windings. They're 90 degrees apart, sine and cosine sort of waveforms. So there's a little summary here. To drive a stepper motor, usually you drive constant currents through the 2 windings. We'll talk about why constant currents are used a little later. The currents are varied and the current direction alternated to cause the rotor to move step by step. For a normal bipolar stepper, the 2 windings are usually driven by 2 H bridges, which allows you to drive current in either direction through the winding. The windings are driven with a PWM waveform, whose duty cycle is controlled by current feedback. By modulating the currents in the 2 windings, the motor rotation can be controlled to finer increments than the mechanical step resolution of the motor, which is set by the motor geometry. That's referred to as microstepping. That's what this shows, the current through a waveform, the current through one winding at 1/8 step, I think. So 1/8 step microstepping divides each 90 degrees into 8 pieces. So the electrical model at its simplest of a stepper motor winding consists of inductance. It's a coil of wire wound on an iron core, and the resistance of the wire. When the motor is moving, the back EMF generated in each coil of the stepper motor presents itself as a voltage in series with the winding of opposite polarity to the voltage that's applied by the controller. If the motor is stationary, the back EMF is 0. So when you apply a voltage to the coil, it's just a simple inductor with some resistance. The current increases with the dI/dt, the amount of current change per unit of time, limited by the winding inductance initially. The bigger the inductance, or the lower the voltage, the longer it'll take the current to rise. The current will rise in an exponential fashion until it's limited by the series resistance of the winding. If the motor's moving, though, there's back EMF, which is proportional to the speed of the motor. Since the back EMF is in opposition to the applied voltage, the effective voltage applied across the inductor is decreased by that amount. That means it takes longer to change the current when the motor is moving compared to when it's stationary. Note that that applies to both increasing and decreasing the current, because in a stepper motor, you need to drive the current up and down. So the supply voltage and inductance control how fast the current can be changed, but the back EMF subtracts from the supply voltage, so it increases the amount of time that it takes to change the current through the stepper motor windings. The motor is moving very slowly. That's really of no consequence. The back EMF is low and the time between steps is long, so it doesn't matter so much how quickly you move the current. So this waveform shows the voltage and current applied to a stepper motor winding at a full step transition driven with a constant voltage. So you can see the voltage is just applied. This green trace is the current. So you can see it takes some time for the current to reach its final value from here to here. If you see the bump in the current waveform, so that's caused by the back EMF. So this is a single step. So the rotor is moving. It starts stationary, it accelerates and then decelerates and then stops at the next step. So this red line I drew on here sort of indicates the motor speed, which is also the back EMF. So the back EMF slows the current rise. As the rotor settles into the new position, it goes to a stop and the back EMF goes back to zero. In this case, the peak of the back EMF is about equal to the applied voltage. So you can see the current goes up and then it levels off. And at that point, the rotor's moving as fast as it's going to move. And the back EMF is essentially the same as the supply voltage. So the current stops increasing. As the rotor settles, then the current can keep going up. So if the motor, same conditions, is moving really fast, the back EMF is very high, and the time between steps is really short. So what that can mean is that the current never gets to the desired level before the next step happens. So this shows an extreme case. This is full step mode, so you would expect the current waveform to be a square wave, but the back EMF is taking away so much of the effective voltage that the current never gets to the desired level before the next step happens. Since the current here is reduced so much, the motor has much less torque than it would if it were moving slowly. As the step rates increased even further, eventually the back EMF becomes large enough that the rotor can't even complete a step and the motor will stall. So if we do stall the rotor, if we lock it in place so it can't move, there's no back EMF. So this waveform shows the exact same conditions, same step rate, everything is the last waveform, but with the rotor locked. So you can see with no back EMF, the current rises in a normal exponential sort of waveform. And it doesn't have that bump that we saw in the last waveform, which was caused by back EMF. So the rise and fall time of the current is still limited by the supply voltage and the winding inductance. So to mitigate the effects of the winding inductance and the back EMF, usually in most stepper motor drives, the windings are driven with a constant current or current regulated driver. To make the current slew to the desired level quickly, a higher supply voltage is used along with a constant current driver. So usually current regulation is implemented as a cycle by cycle peak current PWM regulator. So the H bridge applies the full supply voltage across the winding. That's these yellow pulses. And when the current reaches the desired level, which is this peak, then the H bridge turns off, or in some cases reverses, fast decay, slow decay, for some period of time, then the cycle repeats. So this waveform shows the voltage applied to the winding and an AC coupled view of the current. So you can see the current rises when the voltage is turned on and drops when it's removed. So as we saw, the voltage applied to the inductance of the motor winding sets the amount of time it takes to change the current through the stepper motor winding. We can use a constant current driver to mitigate the effects of back EMF. But even with a constant current driver, the supply voltage will affect the current rise time. This waveform shows the current slewing, full step mode, with a constant current driver and a supply voltage of 20 volts. So you can see the measured rise time of 291 microseconds. And at this point, you see that the regulation is happening, switching. During the time that the current's rising, the driver applies the full supply voltage to the winding. Once the current hits the regulation set point, at this point, then current chopping begins and it regulates the current. So with that same setup, if we lower the supply voltage down to 9 volts, it takes longer for the current to slew. The current regulation point is the same as before, as before during the current rise, the full supply voltage, which is only 9 volts now, is applied to the winding. Once the current hits the desired regulation point, the current chopping starts. So in this case, the rise time is much longer. It was 862 microseconds. So you can see it's starting to look exponential because of the resistance, and the voltage is low enough that that resistance starts to become a limiting factor in the current. So another look at this, we can, as we saw in the last waveform, using a constant current driver, the current can be changed faster, as you can use a supply voltage much higher than what you could apply in a just voltage mode driver. For example, this is a common 2.8 amp stepper motor used for things like 3D printers. It has a rated DC coil voltage of 2.5 volts, but you usually drive it with a 24 volt power supply using a constant current driver. So this waveform shows a full step using a constant current driver. You can see to slew the current quickly, the driver starts out at 100% duty cycle. So the voltage is just solid on at this point. Once the current hits the target, it starts chopping, modulating the pulse width to keep the current constant. So the back EMF generated as the rotor moves is much lower than the applied voltage. In this case, it's maybe 10 or 20% of the supply voltage. So you don't see any bump in the current rise. So constant current drive is only effective in speeding up current changes if the supply voltage is high relative to the back EMF. So this waveform on the left, similar to the last one, but now the supply voltage is only 5 volts. So it starts out applying the full supply, which is 5 volts, to the winding. You can see it stays at 100% duty cycle for a longer period of time because the back EMF is slowing the current transition. So it takes longer to get to its current trip point. Note that this looks a lot like the constant voltage drive waveform, but the top is sort of clipped off. A little bit higher voltage, so 9 volts in this waveform to the right, you start to approach what you would expect, which is a square wave. So you see the current regulation is squaring up the top and bottom, but the back EMF isn't causing such a big bump, but it's still slewing pretty slowly because of the relatively low supply voltage. All right, so now that we know about back EMF and how it affects the winding current, the question is there anything useful we can do with back EMF? So we know that the back EMF amplitude is related to the motor's rotational speed. In fact, it's pretty much a perfectly linear relationship, as this chart showing the motor speed versus the voltage, again driven by that power drill, as that shows. With a stepper motor, though, you already know the speed of the motor, since it's a function of how fast you're stepping the motor. So the speed itself isn't really a very useful thing to be able to measure. However, under unusual conditions, like if the rotor is stalled and you're still stepping, the back EMF can give you some valuable information. So there's a few ways to observe and measure the back EMF of a stepper motor that's actively rotating, except in full step mode, where full current is always applied. There is a period of time when each winding is driven with 0 current. That is, it's not driven. So you can observe the back EMF on an oscilloscope during this time when the winding's not driven. In continuous rotation, when the current in the winding goes to 0, if you set one side of the winding to high impedance and the other to ground, you can observe this voltage. The voltage will drop when the current is switched off and then levels off at a point that represents the back EMF. In this waveform, the motor is rotating pretty quickly in 1/8 step. So you can see that the back EMF settles to about 3.6 volts. So there's other ways to indirectly measure back EMF. Since the rate of change in the winding current is affected by the back EMF, it's possible to infer the amount of back EMF by measuring dIdt during a PWM on time. That method works. It tends to be maybe a little less accurate than directly measuring the back EMF. So given that the back EMF is a measure of how fast the motor is moving, one would be tempted to think that it would always vary linearly with step rate during the zero current period. But unfortunately, it doesn't always work quite that way. So the dynamics of stepper motor operation are pretty complex. The rotor isn't moving constantly. When it's stepping slowly, the speed is pulsing up and down with each step. And as the motor speed increases or a frictional torque is applied, the motion changes, and so does the back EMF. So here's three waveforms, all identical conditions, voltage and current, same motor, at three different step rates. And we're looking at the back EMF during that zero current step. At 400 pulses per second, the back EMF starts out and then sort of tapers down during this time. If you speed up to 600 pulses per second, the back EMF is higher, which one would expect. And it's a little more constant because now the rotational speed is more constant because you have more inertia. It's more continuous motion. But at 800 pulses per second, things change. The back EMF is actually lower than at the slow step rates, and it's increasing over this period of time. So the key takeaway here is that the back EMF measurement isn't simple. Things will change depending on the motor, the mechanical system, the voltage, the current, and the step rate. So if you want to try to make use of this, you need to keep in mind that if you want to get useful information, it's going to be dependent on the setup and the motor and everything else. All right, so in the real world, there's several stepper motor driver ICs that make use of back EMF measurement. One part is the MP6602 from MPS. The MP6602 is a fairly high performance stepper driver, can drive 4 amps of winding current. There's really low on resistance MOSFETs inside. So its thermal performance is very good. So in the block diagram, looks like a normal stepper motor driver, internal current sensing for feedback. But you can also see we're looking across the winding with a programmable gain amplifier and an A to D converter. So that measures the back EMF. So for more details about this part, visit monolithicpower.com. So one of the most useful things we can do with measuring back EMF is detect when the motor stalls. So look at these two waveforms. The first one on the left is showing the back EMF of the stepper motor that's rotating continuously. This we saw before. So you can see there's a back EMF here of 3.6 volts. On the right is the back EMF of a stalled motor. The rotor is locked. So you see the back EMF is 0. After we finish the step, current goes to 0. The voltage also goes to 0. So, since the rotating motor has back EMF, the voltage settles to something other than 0. That value is the back EMF. But the motor that's stalled can't generate any back EMF, so the voltage goes to 0. In the MP6602, the actual back EMF is captured during the zero current steps. Since the back EMF depends on the motor design, the voltage is applied to a programmable gain amplifier that translates that into a voltage between 0 and 5 volts. That voltage, that's right here, that voltage is sampled and applied to an A to D converter. The sample point's actually programmable too, so you can deal with the different sorts of waveforms you find at the zero current step. So once you have that information in the digital form, there's some digital logic in here that processes it to determine if it's really a rotor stall or if it's just, you know, an errant measurement. So there's a bunch of programmable parameters that let you sort of tweak it so that you don't detect stalls unless there really is a stall. In this part, the back EMF value is also available to be read directly through a SPI interface. So that allows you to do some other stuff in a microcontroller. And in fact, you can do torque estimation and other diagnostics by processing that number. So, you know, as we saw, to get any information, the motor has to be rotating. But what about a single step where the back EMF goes all the way to zero between steps? So this waveform shows the current and voltage of a motor that's being moved at like 1 step per second, very slow. So at this step rate, the rotor will come completely to a stop between steps. And you can see when the step's made, there's some amount of back EMF generated for a millisecond or two. Then it goes to zero. In fact, it would actually go below zero, but the voltage is being clamped here. And you see a little bit later, some more back EMF pops up. So what's happening there is the motor is actually oscillating. Magnets are like springs. If you make a single step, the motor will move a little past the step center and then come back. So it rings, and eventually it'll settle down into the new position. While it's ringing, the back EMF will go up and down along with that motion. So if you can make use of this information, it is in fact possible to detect a single misstep in some cases. But there's one problem. Often when a stepper motor is stalled, it's not really firmly locked. Envision a motor that's driving into a stop. When the motor hits the stop, it bounces off. And if you're still stepping, it's going to vibrate. And that vibration will also cause pulses of back EMF that may look very much like this. So that can make it a little hard to detect the stall. Enough programmability, and you can usually find some settings which will allow you to do it. So in addition to detecting the stall, the phase of back EMF relative to the current can be measured to give you an idea of the torque applied to the motor, and also an impending stall when you're getting close to a stall. So as an example, look at these two waveforms of motor current and voltage. The first shows current and voltage. And by the way, these are driven with analog sources, not with a PWM signal. So note that the current lags the voltage by about 65 degrees. The amplitude of the voltage, which is the magenta trace, at the point where current crosses zero, you can look at that point and ignore the oscillation. My circuit was unstable. When you apply a heavy load, the phase shifts about 40 degrees here. So again, if you look at the amplitude of the voltage at zero current, you can see it's changed. It's lower now. So as you apply torque to the motor, the amplitude of the back EMF as measured at the zero current point changes. It decreases. And eventually when it stalls, it goes to zero. All right, so let's look at the back EMF during zero current step versus torque. So here's 3 waveforms showing a motor running at 100 pulses per second with different amounts of torque applied. The voltage is yellow and the current is green, and these are the same between all 3 waveforms. So when there's no torque, in this case, at this speed with this motor, you can see that during the zero current step, the back EMF goes up as the motor moves, then falls a little bit to the next step. So if we apply a moderate amount of torque, it changes the shape of the back EMF curve. the motor settles more quickly and the oscillation's faster. So you can see it goes up and then goes back down and goes up a little bit more. But if you increase the torque even more, so you're near the stall, the motion is slowed even more. So now you're not going to see the rotor go past the step at all because you're holding it back. And you can see the back EMF curve is pretty flat. And it's also much lower than the curves with less torque. Now, again, if you change the voltage, the current, or the motor, you'll probably see different waveforms. So you really have to optimize this for a given setup. The phase relationship of the back EMF versus current can be measured indirectly by capturing the back EMF at a particular sample point. So that'll result in a different amplitude measurement as the phase of the back EMF shifts. Unfortunately, like we saw in these waveforms, the shape of the back EMF measurement versus the applied torque varies substantially depending on the motor and conditions. Since we saw the back EMF varies over time during the zero current step, at what point can you measure it to get the actual back EMF? The answer is it depends. It depends on the motor and the mechanical system. If you pick the right sample point, again, for a given set of conditions, you can get information about the phase of the back EMF. As we just saw, that phase relationship of the voltage and current can be used to estimate the applied torque. You can also get phase information by measuring the back EMF at the correct spot. So these two graphs show back EMF measurement versus applied torque. The first graph shows the back EMF at one particular sample point versus torque applied to a stepper motor that's continuously rotating. So in this case, you can see as the torque approaches the stall, the back EMF drops pretty quickly. So that particular sample point would be useful to detect an impending stall because you'll see a big drop and you'll know you're getting close to the stall. So you can detect it before it happens. But notice that until that point, the back EMF measurement's going the wrong way. It's actually increasing with increased torque. That's because that peak that we saw before is moving, right? So if we move the sample point location to a different point during the zero current step, we get a different result. So if you really want to measure the torque, you need to find the right sample point that gives you an indication of the torque over the range that you're interested in. So that's something you have to do experimentally. And it'll be different for every application. And in some cases, it's not even possible. It's so dependent on what the mechanics of the system are doing in motion. So the second graph shows a different sample point, but everything else is the same. So in this one, you can see as light torque is applied, you see the back EMF dropping. So that setup would be useful to measure torque at lower values, but not very useful for a stall detect because suddenly it's going back up towards the stall. Looks very different than the other curve. So that's why the MP6602 allows programming of that sample point to help get you some useful torque information if you want it from the back EMF. Okay, so that's it for the webinar on stepper motor back EMF. In summary, stepper motors have back EMF like any motor. The back EMF affects how quickly you can change the current in the windings. That can result in poor performance like limited torque or premature rotor stall. Constant current drivers using a supply voltage much higher than the rated DC winding voltage improves the performance substantially, allowing for faster current transitions. So if you measure the back EMF, you can generally detect a rotor stall. In some cases, you can get more advanced diagnostic information about the motion system, including estimating the torque load on the motor. But it's complex, dependent on not just the motor, but the voltage, the current, the step rate, and the mechanical system. So your results may vary. All right, that's it.
Great, thanks, Pete. As I mentioned at the start, and as you see on the screen right now, we are recording this session, and it takes us a couple of days to process it, but we'll then send out an email letting you know how to access it, or you can always check monolithicpower.com/webinars, where you'll see all of our on-demand past events available. Okay, and now we will open it up to questions. If you mouse over the bottom of your Zoom webinar interface, you'll see a Q&A button. Just click on that and go ahead and type it in. Let's see. So the first one that we received during the session, and actually it looks like the same person had a two-parter, was most of the drivers you have been offering are low voltage. What's the maximum speed that can be achieved in ready-made drives available at 48 volts? And then I think they're saying with 5 amps, we achieve 300 to 400 RPMs.
So there are very few stepper motor driver ICs that operate on 48 volt supplies. The bulk of the market is 24 volts, and that's true of laser printers, and it's true of 3D printers and most applications. So I know there are industrial applications that want to run from a 48 volt supply. Off the top of my head, I don't know of any integrated controllers which support more than 35, 40 volts. So it's an interesting point. I don't think it's a huge market, but there's not really any great way to address that. You may have to wind up sort of using a part that uses external MOSFETs and performing the current regulation yourself in a micro.
And then the follow-up on that was even, some drives are available at 72 volts, and that at 8 amps, we get speeds of 300 to 400 RPMs. But
yeah,
same make.
Sorry, go ahead.
Well, just to finish it out, but the same make with a 230 volt or a 110 volt drives, we get 1,000 RPMs, and then looking for drive suggestions there for better speed.
Right. Yeah, definitely. The higher voltage you start out with a constant current driver, the faster you're going to be able to run the motor. I've seen, one simple way to do that is just with a series resistor, and I've certainly seen drives where they're driving a 1 volt stepper motor from a 48 volt source through a giant power resistor, which approaches a constant current drive. But like I say, I think for those voltage levels, there's really no choice other than rolling your own. So the guys that make boxes that do motor drives, that's typically what they do. They'll use discrete power FETs, and they'll use MOSFET drivers, a microcontroller, and shunt resistors to measure current, and they'll implement this whole thing discretely. And that's, I think, the only way, especially if you're talking 72 volts or even line voltage. Yeah, I think that's the only way.
All right, thanks, Pete. And then next one up was, does MPS have a battery powered BEMF driver?
Well, so this part that I was talking about, the 6602, will operate down to 4 point something, maybe a little lower, but it's really targeted primarily at 12 and 24 volt applications. So yes and no, depends on your battery voltage. You could certainly run this part from 2 lithium ion sort of cells without a problem. One would probably not work. We have stepper motor drivers that will work at lower voltages, but not with these sort of features in them.
Okay, and next we had, is there any possibility to detect stall detection during full step mode?
Not with this technique, not by measuring the back EMF directly. The only way you could do that would be to monitor the IDT during current regulation, because once the motor stalls, the IDT will go up quite a lot. This part, the 6602, doesn't do that. There are some other parts that do work that way. But yeah, not this one. I think, in fact, I think automotive gauge drivers work that way. So they're always driving in full step mode, and they just look at the IDT and they know they've hit the limit when the IDT increases substantially. But again, it depends on the motor. You have to have the IDT slow enough that you can make a measurement of it to make that determination.
Okay, and then we also have, how about noise reduction of a stepper motor with these drive ICs?
Yeah, noise is an issue, and there's a few things that can be done to minimize. I'm assuming we're talking about acoustic noise. Certainly, going to higher micro step, like 1/16, 1/32 step, generally lowers the noise. Some of the noise is dependent on the mechanical system, whether there's a gear train or something like that. So to me, less noise, there's a couple things you want. You want relatively smooth mechanical motion. You don't want it to jump and be stepping and vibrating. And the other piece of the noise tends to come from the current regulation itself. That's the kind of noise you may get sometimes with the motor being stationary. Sometimes you'll hear sort of a screaming sound. And that's normally due to the current regulation technique. And in some cases, depending on the way the current's being regulated, you get into these subharmonics where maybe it's going between fast and slow decay at 8 kilohertz or something. And just for mechanical, forget what the word is, but there's motion happening in the winding. So you'll hear it make a noise. So we use a current control method that monitors the current inside the part. So we can bound the current on both the upper and lower limits. So our parts don't usually get into those sort of scenarios where they have a subharmonic going. Still possible. To help mitigate that, this part in particular, you can adjust the off time and the blanking time. So you can optimize those two for a given voltage and motor so that you get smooth current regulation without any of the subharmonic stuff that will make it scream. But like I say, that's one component. The other component is just from the mechanics of moving the motor step by step. And if you're moving slowly in full step mode and you're driving a gear train, most likely it's going to rattle. It's going to make noise just from the motion.
Okay, thanks, Pete. That looks like it was our final question. If you've got one, here we go. The quick one to come in, and if everybody else has one, go ahead and ask away as well. Let's see. So for this one is, suggests that initially use microstep function to build current and then switch to full step to achieve better torque. Does that
Yes.
technology work?
Yes, and in fact, that's a good idea. It takes a little bit of management on the micro side, but that can help to shift step modes when you get going faster and faster. When you're moving the motor very fast, the motor is virtually moving continuously. So full step mode isn't going to really change the motion, but it'll give you more torque. So that does work. And I've seen people do that. They'll start out in quarter or 1/8 step, and once they hit a certain speed threshold, transition to full step. And that does help keep the torque up while you're speeding up.
Great. Another one came in as well. So, and this one was, what's the difference between blank time and off time?
Good question. So when the winding is turned on initially, so we're just activating the winding, the circuit that detects the peak current has to be disabled for a little bit of time, because when you turn it on, the current has a little spike, and that spike is mostly caused by intra-winding capacitance. So I didn't show it in the model, but that stepper motor model, there's also a small capacitance across the winding. So when you first turn on the winding, there's a big current spike which goes to charging that capacitor. So what we do is we blank that current detection for some period of time. Otherwise, it would trip off immediately. So after the blanking time expires, then we start looking at the comparator that monitors the current. So the blanking time is that window where we aren't looking at the current. And then the off time is the time after we hit the current limit, we turn the winding off for a fixed period of time. So the combination of those two will set the switching frequency. The blanking time, since we're blind during that period, also is a minimum on time. Because once we turn on, we're not going to turn off until that blanking time expires. So in some cases, that means the current may overshoot a little bit. And we have ways in the current control mechanism of bringing it back down. But that's what those two times are.
Okay, it looks like that is all the questions for today. So once again, thanks to everyone for joining us. We will send out an email with all the materials shortly. And please look forward to other future webinars that we have coming in the future months. All right, bye everyone. Have a good day.